Not this one.
Yes. This one's a MEMS device case.
No, no. I mean, why is it different?
Oh, sir, I've changed slide size because of camera.
Okay. Good morning. Next will be our lecture number 13 on the case study, MEMS device case study. So I will share about a number of MEMS device from the beginning of the design, simulation, and processing or fabrication, assembly, then characterization of the device. So this will be, specific case study. Firstly, on the PZT, piezo-driven silicon XY microstage. PZT is the piezoelectric materials. Then will be assembly with a silicon XY stage. And the objective here is to design the microstage for the application of certain positioning. So this will be the content of this case study. Construction of, I will introduce the construction of XY microstage, the design consideration and simulation of the XY microstage, as well as the piezoelectric. Of the piezoelectrics, and the fabrication process, silicon XY microstage stack piezoelectric actuator, and the integration process of the XY microstage. And the multi-probe data storage as a background. Why we try to design this XY microstage is because with the intention to use in the multi-probe data storage. Multi-probe data storage is in this kind of data storage, and with a lot of probes to read the information from the substrate at the bottom. So this XY microstage has to make a movement of in the lateral XY direction in order for the chip to read the information on the stage. So the positioning of the microstage is with the accuracy less than 25 nano. So here the objective is to fabricate a PZT-driven or piezoelectric-driven XY microstage for the use of data storage with the compact size of 20 times 20 millimeter, large displacement of more than 80 micrometer, and a high resolution, 25 nanometer of resolution, I mean the stepping of the movement, and low cost, which is something that can be realized by the MEMS process, microfabrication process. So this is to benchmark before we proceed. So this kind of microstage to have X and Y movement are available. So for example, with a thermal actuation method, the displacement can be in the range of 50 to 60. Let's say this is 52 in the X direction and 60 in the Y direction. But somehow for this design by Herbert, the area efficiency is less than 5%. I mean the usable area of the microstage. And in the design of using actuation method of electrostatic, so a higher displacement can be met, a larger displacement can be met up to 110, for example, by Sasaki, and 12.5 by Liu. So, but here you see that the area efficiency is low as well, with 8% and 6.5%. And electromagnetic, it can make a large displacement as well, 120 micrometer, and the frequency is about 150 to 170. And here, I mean, I forgot to mention that electrostatic, you have a high frequency of 500 to 700 hertz. Then, and piezoelectric, which suffer this displacement of 2 micrometer only. With, however, you see that in terms of the design of microstage using piezoelectric, you can have higher area efficiency in comparison with the rest. This is due to the compact of a piezoelectric material that can be used in comparison with electromagnetic, which require a lot of space. Then you sacrifice the area that can be used. I mean, the efficient area that can be used. Same goes with to the thermal and electrostatic actuator, with also require a lot of space. Then you don't get your area as intended for the usage of the microstage. So this is the microstage architecture. So the proposed design of the silicon microstage with a three main component of the microstage. You have a piezoelectric, you have the silicon stage itself, then with the capacitive sensor at the back. So this capacitive sensor will detect the movement of the microstage here. So as I mentioned, the piezoelectric actuator coupled with silicon, then you have capacitive sensor at the back. So, however, I mean, as mentioned before, piezoelectric suffer from a very small displacement. So, meaning to say it cannot make, even though you can exert high force, but displacement is very small. Therefore, the design has to include certain means where possible in order to increase the displacement or the lateral movement of the stage. Here, the amplification mechanism is introduced here, what is called as a Mooney amplification mechanism, in order to amplify the displacement here into a bigger displacement. And what need to be considered next is on the blocking force. So blocking force meaning you have to have some means of handling or uh, to maintain the position of the stage and to make it robust as well. So kind of, let's say here you need to have a support a mechanism in order to get the position. Then of course, in order to make a movement, you have to overcome this spring constant of the support. And for this Mooney mechanism, it need to be flexible enough, but at certain extent robust. So that to allow movement for flexibility, but robust to allow to make sure that it won't break if it's in operation. So the support spring, flexible but strong and robust in order to hold the stage and also to return the stage to its original position. So that is the consideration need to be given in order to have this design of the microstage. Here is the zoom of the Mooney amplification mechanism. Here is the zoom at the support spring. It's a serpentine spring. And this is the hinge of this Mooney mechanism. So this need to be designed accordingly so that it's robust, and at a certain extent you can you have the flexibility to make sure the exerted force can make the movement happen. And this from the beginning we can calculate the Mooney structure performance. Basically, the structure design is critical, and we need to make sure that the movement, and by calculation, because we want to have certain displacement or distance to be displaced, then we need to calculate how how much will be the possible movement of the stage later on. So with the calculation of this piezoelectric, then let's say a few micron here, then what is the maximum of this displacement of delta M? So now the calculation can be done with the constraint of the size, etc. It need to be calculated. So the amplification factor of a Mooney mechanism here. So we have a Mooney amplification mechanism. Then let's say here, this is the FEM simulation. So we know that by decreasing the angle here, theta, we can get higher amplification, nearly 20 times amplify of the movement. So, but this is geometrical analysis, so it do not take care of certain parameters here. That's why you can see that is kind of not that accurate after certain degree here. So this is the amplification mechanism that you can calculate according to numerical calculation. So, but the FEM will show more accurate, where you can see here about 20 times of amplification can be made by about 0.5 degree of this angle. So in terms of design and simulation, so we need to calculate this, for example, the stiffness of the system using Mooney mechanism, and with this, the Mooney stiffness by FEM is as shown. So stiffness is quite important here, because we want to make sure if you have your piezoelectric to be here, you can exert enough force to overcome the stiffness. So that is where the design of this amplification mechanism need to be calculated in terms of stiffness. Then we have the support spring as well. The support spring also need to be calculated in terms of the stiffness of the spring. So the spring constant of the serpentine spring can be calculated using this equation. Then the Young modulus of silicon, we know the property of silicon, 100 gigapascal, and the number of beam here, 1, 2, and 3. 3 beams. Then for 2 set of support spring, which is 1 and 2, 1 to the left and right. Then we can calculate the total, which is this will be the equation to just add on with the total number of spring. So the stiffness of the support spring is calculated to be 99 Newton per meter. So this is also a simulation have been done in order to look into the force exerted and force required to overcome the support spring. So with this, we can have a proper design of the thickness. Let's say here, with the thickness of 50 micron and the length of 400 micrometer, and this thickness of 400 micrometer, that is where you can get the spring as intended. So this can be changed accordingly by design using calculation and simulation to see what is the stiffness of this spring, if you want to have a stiffer or less stiff spring constant here, according to the needs in terms of piezoelectric force exerted. But at the same time, we have to make this robust enough, and also we have to consider the processing capability, which is to make the thickness of 50 micrometer is a quite challenging process. Meaning to say, to reduce below 50 micrometer might be very difficult. So this is the stiffness of the Mooney mechanism. Overall stiffness, because we have the stiffness on the Mooney side as well, not just the support spring. then the total stiffness is K stable stiffness of 1599 Newton per meter. So the resonant frequency for the inner stage and outer stage are calculated to be 620 Hz and 485 Hz. So because this is the formula for the resonant frequency, you can see that the inner stage is smaller in comparison with the outer stage here. I mean, the X direction stage is bigger, so it has a higher mass here. So that's why the resonant frequency is different, because the mass is different for X and Y direction stage. So this is the calculation of the blocking force. So you have a blocking force, meaning the force that need to be overcome, the stiffness of the system. So the blocking force that need to be overcome when you have the Muni degree less than 2, let's say from very high 0, 0. This is 1 here, and it go down. I mean, meaning to say, if you have your angle of the Muni smaller, then your blocking force is much higher. So that is where you need to have a trade-off in order to design this Muni not to be too small angle of Muni amplification mechanism, but to have a trade-off between the blocking force and also the amplification factor that you might obtain. So then the next thing is the design consideration for the PZT actuator. So coupled to amplification mechanism to produce large displacement. So basically this is the design of amplification mechanism, PZT actuator. So with 8 millimeter length with the thickness of about 400 micrometer, and we have the design in order to make a higher stroke or higher displacement of this actuator is made into interdigitated electrode. So you have a piezo ceramic PBZRTIO3 here, the material, ceramic material, and with interdigitated nickel electrode deposit on this in between of every layer. So the distance between the pitch of this layer is 100 micrometer, and the size of the electrode, nickel electrode, is 30 micron or 30 micrometer. So what need to be considered in this design is we have to know the stroke of the stacked PZT actuator. With this length, how much displacement can be made, and the resonant frequency of stacked PZT actuator, energy of a stacked PZT actuator, and the force exerted by the this actuator. So now we calculate all the parameters, the displacement, the stroke of the actuator, delta L equal number of layer times the piezoelectric coefficient direction of D33 and voltage applied. So here we can see that the applied voltage increase, then you can get your displacement increase. So just a comparison of two types of, layers, the N, the layer here. So N equal 50, you can get up to maybe 3.2. N equal 58, you can get about a 3.6 at 100 volt. So that is the difference between these two number of layers. In this case, N58 with D33 of 6.35 Armstrong per volt, using the materials by NEC, then the calculation shows that at 100 volt, the displacement is approximately 3.7 micrometer. Then we calculate the force of this stacked PZT actuator. Force exerted by the stacked actuator here can be calculated using this equation, where E is the Young modulus of the material, A naught is the original cross section of sectional area, and L naught is the original length, and delta Li is displacement of a PZT layer. So with this, we can calculate the exerted force of this actuator. And for this design, we have A naught T times H, which is the size of H is the thickness, 400 micrometer, and the thickness, the width is about, I think, about 400 micrometer as well. 8 micrometer. Okay, and L1 is 0.1. So with this calculation of W equals 0.8 and W equals 0.6 comparison, we know that the exerted force for 0.6 W here is about 10, and if you have a bigger size, 0.8 millimeter of W here, we can have higher force, which is at about 13 Newton. So that is where we can have a 14 Newton here. Then we can calculate the resonant frequency of the system using this equation. And we know that it involves the material mass as well. And we can calculate the stiffness, the actuator, and also the effective mass of the actuator. So the calculation with this information, we obtain that the effective mass is 2, and the stiffness of actuator 2.9 times to the 10 to the power of 6 Newton per meter, and resonant frequency of 108 kilohertz. And then we try to couple this information of PZT actuator properties in terms of exerted force, displacement, etc., and to couple with the microstage where you have the information of the spring stiffness and Muni stiffness, etc. So for Muni angle of 2 degree, for example, the maximum stroke of the actuator is rated to be 2.8 micron. So the actuator blocking force is here. So 2 degree of 2 degree of Muni angle here, then you can obtain 2.8 times 18, because the amplification is 18 times for the 2 degree of Muni angle. So it's expected to overcome the spring actuator blocking force and the spring, so you can get some displacement of 50.4 micrometer. Then this is the performance that can be calculated from this design. We have different in terms of X and Y direction for these two stages, because this different mass. So for this, the Muni angle for X direction is 50.4. It's the same because it's the same spring constant, etc. Mass is not in part of the equation for the displacement, and stiffness also the same. And because the different mass in terms of this design, the resonant frequency will be different in terms of X and Y direction stage. So now we look into the fabrication process of this micro stage. We started with a silicon substrate, then with a thermal oxidation to have a silicon dioxide layer on both sides, top and down, because later on we will have a circuit design on both top and down of this device. Then we sputter chrome gold, a layer of chrome and gold on both sides, because the requirement for electrical circuitry. Then do the photolithography to pattern for electrical circuitry. Then etching to remove the materials to pattern. Then remove photoresist here, and do photolithography again in order to remove the silicon dioxide layer as an opening before we do the structural etching. So then we do deep RE, reactive ion etching, as I mentioned before. So with this reactive ion etching, this can be etched, the silicon can be removed in order to have a structural design. So then we remove SiO2, silicon dioxide at the bottom side. Then we remove all the photoresist and get the structural design of this. This is the top side of the device with a Muni amplification mechanism. This is on the back side. So you can see that on the back side, that is electrical circuitry of the capacitive sensor. So this will be a sensor that can detect the position of the stage later on. So this is kind of a special design of the capacitive sensor. Next is on the detail of the fabrication, what we obtain. So as I mentioned before, it's quite difficult to obtain a good structural geometry when you do the process. So however, this is relatively good with a 50 micrometer width of the support spring, the serpentine spring. And this is the hinge, where you can see that the electrical circuitry, the chrome gold pass through this small area, narrow area of the hinge to go to the this part of the actuator in order to supply the current to the actuator later on. It's passed through this area and go to the actuator. As can be seen here, you have a bonding pad and a circuit design that go through both sides of this area in order to have a pole of negative and positive to the actuator. So now the process of fabricating the PZT actuator, the piezoelectric actuator. So the process begins with the bulk PZT, then the photoresist coating here on the top of this substrate PZT, then formation of groove, and this is using dicing. The groove is using mechanical dicing, which removed by force 30 micrometer width of dicer blade. Then we have a seed metal deposited using sputtering, and this is covered by coating because we want to prevent or remove the metal later on the top side. And there is a certain pattern so that we can connect to electrical wiring in order to do the electrodeposition later on. So the at the bottom side of this trench, we have a seed layer of metal, and of course, some might be at the wall of this trench. Then we try to do the electroplating later on. We remove this and do the electroplating to form the electrode to grow the nickel from the bottom of this system, this trench. Then we do the polishing for both sides of the PZT actuator. Then we get this kind of PZT interlayer between nickel and ceramic PZT. Then we do the patterning on top of this PZT in order to have, you see that the opening is, this is on one side, you have one open, one cover, meaning to say we want to have this positive and negative interconnects so that it become electrode for the actuator. This is using polyimide as the insulator layer. So then we deposit metal after the polyimide. So this metal will become the electrode for the interdigitated electrode of the actuator. Then we do photolithography and dicing. Photolithography to have the opening. So because this metal deposition is on top of the whole system, the whole substrate, then we do photolithography to have this kind of interconnects. So because we have a positive and negative interconnect, so this is interdigitated. You can see that this kind of opening is basically to have the electrical circuitry to be connected to the nickel electrode. So the nickel electrode is connect on the left side and the top and the bottom uh, interdigitated manner. So they will form a positive and negative electrode to the system. So see here the electrode is about 130 micron in terms of the pitch. So this need to be integrated together between the stage and the piezoelectric actuator. So how this can be done? So the process of integration here, we have a piezoelectric actuator, then we have a silicon substrate or silicon XY microstage, then with a positioning sensor as well at the back. So a, a, a way to position the actuator to the stage will be something crucial in order to place at the good place. So the alignment of the actuator by photolithography is made in order to provide a accurate position of the actuator. So this is the figure of piezoelectric actuator slot into the position. So the process of integration, so we have to prepare the silicon, the silicon microstage here. Here, the silicon microstage need to be processed again. So this is quite challenging because you have everything in the dimension, the 50 micron, for example, it need to be handled with care, especially when you do the electrospinning in order to deposit photoresist on top of this material. So the silicon stage firstly attached to a silicon substrate because this stage is quite fragile and you cannot handle it without a carrier. So this silicon substrate basically act as a base carrier in order to do the processing. Then after photoresist and photolithography, cover certain area using photoresist and do provide opening at certain area. So then do the seed metal deposition on the side which is open with a gold chrome. Then with this, we cover again with a photolithography to cover a certain area so that later on when we grow nickel, it won't affect at the some other place where you have a metal contact. So here you can see that some opening of the photoresist and silicon and the opening of 400 micrometer thickness. And you need to remove this photoresist of the sidewall. So this is a quite a challenging process. Remove the photoresist, then try to deposit nickel gold in order to provide conducting surface in order to grow the nickel later on as a bonding material with the electrode, with the piezoelectric. So this is the process of integration. So align PZT with a actuator to the XY stage. You have a PZT actuator here, then align well with the micro stage. Then try to place it accordingly. We use piezoelectric actuator coat with photoresist as well. Why is it coated with photoresist? Because we want to make sure that to prevent later on the process of electroplating might grow nickel on top of exposed surface of the contact. I mean the metal surface of the piezoelectric. So this is a piezoelectric actuator attached to this microstage in this manner. Then remove photoresist. Then it's attached. So this is what happened. A piezoelectric actuator at Y stage do nickel electroplating here in order to connect this electrical circuit of the piezoelectric actuator as well as to the stage. So this is a stack actuator. And this is the nickel that electroplated to the as a bonding material with a stack actuator. Then we go into the experimental result. But before we use the fabricated actuator, we have do experiment with the commercially available piezoelectric actuator, but we slightly modify because it need to be slot in with a narrow area. So this is has been thin in order to slot into this stage. So the SY micro stage and the modified commercial actuator. So this is the result of the displacement in X and Y direction. So, but this displacement is quite big because we are using a big commercially available actuator, and it can do quite exert quite big force and displacement because of the size is bigger. Then what was obtained, the displacement of 82 micrometer. So if you remember previously, we have about 58 micrometer only this displacement, but here is a 82 because the use of high force exerted piezoelectric actuator, you can overcome the spring constant, then you can have a high displacement, larger displacement. So even though at a 70 volt, this is a 82 micrometer. So large displacement compared to the driven by fabricated actuator due to large stroke of actuator here. So here you can see hysteresis. As I mentioned before, this is piezoelectric actuator properties, the direction of displacement, the expansion, and the direction of contraction. I mean, it doesn't follow the exact route, but it has this kind of hysteresis feature. So the actors to a stroke of 4.5 micrometer basically result in overall stage of movement of 82. So this define the amplification factor of the Mooney. So about 80 as predicted by the, predicted by simulation. So the simulation predict when we have Mooney angle of 2 degree, we can get 18 times of here. I mean, this is a simulation. This is Y and X direction is almost the same, but this is, agreed well with the simulation result. So, and this is the Mooney amplification mechanism, prediction. The Mooney angle of 2, simulation predict of 19, then experiment we get of 18 times. So this is, can be said to be well agreed in terms of simulation and experimental result. Then we look into the resonant frequency of the system. Of course, experimental result yielded resonant frequency of 361 Hertz. and 642 Hz in X and Y direction respectively. Low resonant frequency in X direction due to added mass by commercial actuator. So the commercial actuator is much bigger, then the mass will be added. I mean, additional mass will be there. Then, of course, with mass, you have a lower resonant frequency of the stage. So this is the fabricated XY microstage with, in comparison with a coin, Japanese coin. Then you can see this actuator, stack actuator connected with a bonding pad. Then this is the PZT actuator, but in this case, silver paste was used in order to bond. So this is the result of this microstage using in-house fabricated actuator. Some displacement can be seen. Okay. So the result here is a displacement of approximately 16.5 micrometer was obtained at a bright voltage of 60 volt. So small displacement due to actuator stroke. So the actuator stroke itself is quite small. So the amplification is right, 18, but it's also about the exerted force of this actuator as well as the actuator stroke. So you can see here, the stroke is about 16.5 with the hysteresis feature of the piezoelectric actuator. So an amplification factor of approximately 15 was obtained, slightly low compared to simulation result, which is 18, might be due to fabrication issues. So this is the challenge of fabrication. So the dimension might be not everything the same. So if some changes, let's say the hinge of 50 micron becomes 60 or 55 micrometer, and here might be different little bit. So that will kind of make the things different. So the resonant frequency of 456 Hertz. So it's a good agreement with analysis, calculation, because in this case, the actuator mass is very small in comparison with a commercial actuator. Then there is no added mass, highly added mass is just a very small mass that agreed well with the simulation. So here in this case, we have fabricated the multi-probe XY microstage, which you can see here, the piezoelectric actuator can make a displacement of 82 if you use a better actuator, but in this case, we use the stack actuator, which can produce a lower displacement. Then it end up 16.5 only. But if you can get a better actuator, then you can go up to 80 micrometer of displacement. And this is the frequency of the system. But here, you can see that area efficiency is much larger in comparison with the rest of the design. So, achievement of this design with a possible resolution of less than 25 nanometer, because the PZT has a very accurate minute of displacement, and travel range of 80 to 100 micrometer might be possible if we use a good actuator design. Then this will be the things that is possible. So this is what we have achieved for this PZT hybrid microstage. Now, the second case study is on the micro energy. So micro energy conversion is a device that convert some environmental energy into useful energy. So we try to design and fabricate such a system. So this micro energy has a very huge market, basically. The global energy harvesting system market size with a value of 452 million USD in 2020, and is expected to grow at annual growth rate of 10.2%. So this is the global energy harvesting market, 452.2 million. So the growing application of the Internet of Things, including smart cities, smart home, industrial IoT, and machine-to-machine communication, among various others, are further expected to drive this market. So the micro energy, which require a very small energy to operate, that produce a small energy but sufficient for certain sensor to operate, is the choice of system because of its small size. Factors such as growing environmental awareness, supportive government policies, and greenhouse gas emission reduction targets, and rising demand for energy are expected to drive the market over the forecast period. So here, the objective of this design is to develop a process for fabrication of microarray directly on flexible electrospun beta phase PVDF film. So this is a PVDF flake or material. It's a copolymer, the most extensive studied polymer for piezoelectric, and high resistivity towards most chemical, oxidant, and intense ultraviolet light. And PVDF have 5 different polymorph, which is alpha, beta, gamma, delta, and epsilon. So the most influential and typical phases are alpha phase. The axis of the change and the dipole component are anti-parallel, thus neutralizing each other. And the beta phase, the dipole components are parallel, hence result in greater spontaneous polarization. So this type of conformation displaying pronounced ferroelectric and piezoelectric properties. So this is the process of to synthesize the PVDF thin film. So synthesis of high beta phase content PVDF film using electrospinning. Then the beta phase fraction of the, this is electrospinning process. So beta phase fraction of the electrospun PVDF film will be determined using Fourier FTIR spectrometer and XRD. Then micro-patterning, then an integration with the device. So electrical performance of the energy harvester will be evaluated. So this is the produced PVDF membrane with about maybe this is about 80 to 100. This is about 200, right? 200 nanometer of diameter. So this is the design microarray. So after the deep RIE. So this is the process of producing this PVDF using electrospinning. Using electrospinning with a PVDF solution inserted into this shrink. Then there is needle here. Then you apply high potential of 10 to 15 kilovolt. Then this drum rotate. Then you can get your membrane of PVDF. So the PVDF synthesis was intended for the beta phase PVDF because of the high piezoelectric component in the beta phase. So with the process of electrospinning just now, here, with the high applied voltage, this can be make the process easier with a one-step process to produce a beta phase PVDF. So then the experimental work we have the flexible substrate, then adhesive, then attach the electrospun PVDF on the adhesive of the substrate. Then with a stencil mask, do the patterning of the stencil mask, then micro patterning of a PVDF array using, to micro pattern the adhesive first, then, micro pattern the PVDF using deep RIE, then later you need to micro pattern or remove the adhesive as well. So the preparation of this material, pre-baking and flexible substrate at 65 degrees Celsius for 2 minutes, then spin coating of a photoresist SU8. This is quite a high viscosity photoresist at 2000 RPM, and handling rolling electrospun PVDF film on the photoresist coated substrate and curing for 4 hours at 80 degrees Celsius in oven and micro patterning using RIE. So as I mentioned before, then we get this PVDF, electrospun PVDF with a thickness of 50 to 70 micrometer on the SU8. Then we have a stencil mask here. Then the electrospun PVDF. Then what was obtained is this kind of design, basically with a clamp to the PVDF membrane to the structure. The electrospun PVDF here, this is a stencil mask. Then we pattern into this, and this is the actual, these two are the actual image of the microarray with about 200 micrometer width and about 400 micrometer length. So this is the electrical circuit that connects each of the array. So some voltage generated, using simulation. So we can see that if we apply hot air to the system, then we can have PVDF to be respond to the temperature, then you can harvest electricity as well as respond to the strain by the flowing air, the force, then you can harvest electricity as well. So this is the property of the beta phase material. So the micro pattern of the PVDF membrane again. So the result. Okay, this is the actual thermal image of the micro device at room temperature with the applied hot air 34.5 degrees Celsius. You can see the different gradient of the temperature here. So the fabricated PVDF is placed in this manner. Then we can harvest some electricity. So the VOC is 1.4, about 1.4 volt per meter square. So this is with the wind speed of 1 meter per second and the temperature of 310.15 Kelvin. So that is the result of this micro device. So with this micro device, we can harvest sufficient power output to run a very small sensors, for example, in order to provide mobile power to the device. So, however, the use of PVDF might need to be redesigned in order to have a higher power output in the future. Okay, any question from the floor? Yes.
Any type of unexpected failure made in MEMS?
Yeah, unexpected failure happen along the process as well. Basically, the process is very much a skill process. even though you have the machine, etc., but the handling and how you attach your substrate to the materials and how you apply the photoresist also depend on skill, because a human have to do all the process manually. So that is where unexpected process, if you don't really careful, it might break some of the components, the intended size was not obtained, for example, and the process does not go well in order for you to produce certain dimension. So that is part of the challenge in MEM process.
So, is this MEMS can be scaled up for mass production?
Yes, MEMS, as you are aware, is used wafer fabrication process. Wafer, so silicon wafer. I mean, it depends on the substrate material, but sometimes you use glass. Sometimes it depends on the application, whether you use glass or you use silicon or you use some other substrate such as flexible substrate polymer. So it can be used as well. But the thing is, it's cater for the process batch processing, because the system is initially from the use of chip design, I mean chip fabrication, semiconductor process. So semiconductor process is batch processing, where you use, let's say, 4-inch or 12-inch wafer. So you have many device on the wafer. So that is what we known as the batch processing. Thank you. Yeah. Yeah. Thank you very much. I think that's all for today. Thank you.